That's a good thing to see, that so many people are interested in doing CMake right. My name is Deniz Bahadir. I'm working at Banox. We are a small company trying to speed up the internet. And if you want to know more, you can ask me after the talk. But now we will talk about modern CMake and especially about more modern CMake, pun intended. Okay. I guess most of you probably know, but maybe there are some people who don't. So let's start with what is CMake. And to say it simply, it's just a build system generator. It's a build system generator, though it's not a build system. That's a different thing. It generates the input files for other build systems, like, for example, Make, Ninja, Visual Studio, Xcode. So CMake allows you to generate the files for your favorite build system you want to use. And because it supports so many build systems, it also supports several platforms. It can run on several platforms, Linux, Windows, OS X. There might be some more I don't know of, but these are the most presently known. And it also supports compiling cross-platform if the compiler that it uses supports that, of course. And most interestingly for us, it supports several languages and, of course, C++, but also Fortran, C#, CUDA, and I heard it even supports Java, but who wants that? Okay, so we can generate the input files for build systems. That is good to know. When did it start? So let's start with a very, very short and brief history of CMake. It started around 1999 or 2000. Not really sure. In one of these years, the first release came out, and that's definitely not modern CMake. That's really old one. I think that doesn't even work today anymore. While the term modern CMake came up with release 3.0, some people might say no, it was 2.8.12, but let's say it's 3.0, which was released around 2014, and it has a completely new concept, which is everything is a target, and it's a self-contained target, so it knows everything it needs to be used, and everything it also, of course, needs to be built before that. And then we had several releases since then, and since release 3.11, which was released in March of this year, some of the some of the commands that didn't work quite the same, that didn't work uniform with all these different targets and parameters, these problems were unified, so the commands work now as you expect them to work. And with CMake 3.12, which was released in July of this year, some of the last big left-out tasks were completed, something a lot of people complained about. And I will show you these things and how you should use them in this talk. And for that, I will refer to the old version of old style of using CMake as traditional CMake. Then, of course, modern CMake, since the term was used. And with the latest releases, I'm talking about more modern CMake, although, of course, it's still modern CMake, but doing it a little bit more modern, more fashioned way, say it like this. Okay, to understand my talk, you need to know just two small things, and these are the build requirements of a target, what that is, and that is just everything that is needed to successfully build the target, so the requirement for building. And that could be, of course, the source files, but also the include search path, the preprocessor macros that need to be defined to successfully build. Of course, your dependencies you have to link to later, some compiler and linker option, as well as features, for example, that your compiler needs to support C++11 or something like that. So these all are build requirements to successfully build a target so that your program also becomes what you want to do, what you want to have, which is a running program on the machine. While maybe you don't only have a program, you want to compile a library, and that should be used by other programs. And for that, we have the so-called usage requirements, of course. And this is everything that is needed to successfully use that target. And that's pretty much the same as you see here. And as I said, you want to use it especially as a dependency for another target. So if you have a program that has a dependency on a library and you're building that library, this has some usage requirements to be used by that program, by that other target. And it's pretty much the same. All those source files, in general, you don't need them then anymore because you already compiled them. But still, that's fine to have and to know. So with these two things, we can just jump right in. And your first question would probably be, okay, you say traditional CMake, modern CMake, what's the difference? Let's look at a small, short comparison there. If you are looking at where are these build requirements for a target set on, in traditional CMake, you do it on the environment mainly, not only, but mainly, which means these settings have directory scope. So you are doing all the stuff in a CMake lists.txt file. And if you set a requirement there, a build requirement, it is not only for one of the targets, it's for all targets defined there and all targets defined in subdirectories defined there that you're later on processing. Not in the ones above, but in the subdirectories. While in modern CMake, you can be more specific and set these build requirements directly on targets themselves. Sometimes you don't even have to set them, and that's the most important thing of modern CMake, because they come automatically by the dependencies of these targets in form of the usage requirements. And if we look at how the usage requirements for a target are kept track of, in traditional CMake, you do this mainly by variables or cache variables so that it's globally known. And you can run CMake several times and still the same variable is known. While in modern CMake, you're using targets. As I said, they keep track of the usage requirements themselves. And that's the big thing of modern CMake. And the usage requirements, they have to be propagated from the dependency to the user, to the other one depending on it. And for that, we have the command target link libraries and to declare such a dependency. And in modern CMake, that's a great thing. The propagation of usage requirements to make them become the build requirements of our new target is automatic. You don't have to do anything. While in traditional CMake, a lot of stuff there you have just to type in your hand again, typed by hand again. So the only thing that's automatically propagated are the path to the library files, so what you are linking. But everything that it needs, for example, some special compiler switch, some feature the compiler needs to know, needs to support, they include directory or what else, that you have to propagate by hand. That's not done automatically in traditional CMake. So this is the big difference there. And overall, we can say because of this, the traditional CMake is more error prone. It's easier to make some errors, especially, for example, if you're relying on a variable and that variable you think is set, but it just evaluates to nothing, and then you don't have the link dependency you're expecting there to have, or the usage requirement of it, and it doesn't work. While on modern CMake, this cannot happen as easy. It might happen. There are still possibilities to do it wrong. But it's easier to do less errors. And it's also possible to be more fine-grained, to do a better configuration, to say, okay, it's just for this target. The other ones don't have to know this. Just this target needs to know. Okay. And for that, in modern CMake, we have several commands to set the build and the usage requirements. And they all start with target underscore. These are the ones that are currently existing, or the latest ones will be existing with the next upcoming release, 3.13. 13. I'm not sure when it will be released, but it should be within the next month, I guess. And the syntax is always the same. First, your command, then the parameter. The first one is the target you are setting this one on, a keyword, and then your requirement you are setting. And the thing is here, for setting the build requirements, you are using the keyword private. Simple. It's just the private thing for them to be built. While if you're setting the usage requirements, you instead use the keyword interface. It's a thing. And of course, you want to maybe sometimes set both. Then you would use another keyword, which is public. So these three keywords you will see very often in modern CMake. And that's what you have to use there. And you should always think of using this keyword, especially if you're using the target link libraries command. especially because that one is really, really old. I'm not sure if it even existed in the oldest CMake version, but it exists for quite a long time, even before the concept of the target things and so on. And so it works also without the keyword, but never, never do this. Never use it without the keyword if you're trying to write modern CMake. And you should do that. So never forget the keyword. But, sorry, what?
Is that default if you leave it out?
But there is no default, but you can just leave it out. The other ones will complain, so CMake will complain, hey, you're missing the keyword there. While on target linked libraries, it works, and it has some behavior that is also defined, but it's not what you're expecting with modern CMake. So just a simple rule, never forget the keyword. Okay, with that, you want to see the differences, I hope, for traditional CMake to modern CMake to more modern CMake. And for that, I'm trying to demonstrate this on a small example project, which I call the calculator app there. Although it's not a real project, but you can see everything there. I have the examples online, so if you want to test it yourself later, you can. And this here on the right-hand side is the directory structure. And first, we think of, okay, we want to have some calculator that someone can use for free, and we create a free calculator, and this is done in the app subdirectory, and it's defined and declared in the CMake list txt file there, and the sources are below that. We don't care about the sources now, we're looking just at the CMake list txt files. While again, there might be something you want to earn money with, so that is in this case the premium calculator, which has some extended functionality, and this is not free. So you want to earn money with that, and that's just fine. You can also declare them in the same CMake list txt file, and that is done in the app directory. Both of them need dependencies, and both of them have a dependency on Boost program options to successfully parse command line. And the targets for Boost, or this information where you can find the Boost libraries, that's coming from the external Boost subdirectory, and it's defined there in the CMake list txt file. Then again, they have some functionality you yourself of writing, so some common library or some libraries they are using, and the free calculator uses the basic math shared library coming from the library subdirectory, while the premium calculator uses the math for extended math library, which has some extended functionality. And for having this extended functionality, it also has a special requirement. In this case, it's Boost Graph for our example. So this is what the different calculators require, and that's where we find this on the right-hand side. And then all of these targets, maybe the libraries or the executables, they have a dependency on Boost Outcome. If you don't know Boost Outcome, it's a header-only library by Niall Douglas, which was reviewed and now should become a part of the Boost collection, but still up till now there's no release with it. So that's a special thing. We have to find it separately from the Boost libraries. Okay, that's how our structure will look like, and that's what we do. Let's go on. First, we want to find the dependencies, and in this case, it's Boost. We are looking for Boost. How do we do this? In traditional CMake, as well as in modern CMake, we use the find package command, because CMake comes with some so-called find Boost CMake script, which helps us finding that. First, you just have to define some variables there which say, okay, which version of Boost do we want to have, the dynamically linked or the link to the static runtime, what version. Maybe it's a version the find script doesn't know, so we have to add it additionally for what compiler maybe, because it has some special index. If we have set this, we just call the find package command, and hopefully it will find what we are looking for. And in this case, we are especially looking for the program options and the graph library from Boost. We are handing this especially there because they are really shared libraries, or they are libraries at least, linked that have to be linked, while a lot of stuff for Boost is header only. There we don't have to look for that, especially because if we find the include directory, in general we should have found them. But in this case we are saying, okay, we are looking for these specifically. And then if we are successful, the script will return, say, hey, found Boost, great, and I have these two variables for you, Boost include dirs, which will contain the include path to the Boost libraries, and Boost libraries variable, which will contain the path to the library files you are linking to. Note, however, both libraries we have looked for, program options and graph, are stored in this single library there. If we're using modern CMake approach, we even get more, which is the so-called imported target, which is the same as any other kind of target, except for the case that you cannot build it because it's already built. But you can use it like that. And in this case, we have these three imported targets, which is boost, double colon, program options containing the program options library and the usage requirements. It has everything that you need to have to link successfully to that. Similar for graph. And the boost, double colon boost thing, that is just the target which has the usage requirement to successfully use the header-only libraries of boost. So these three things we get back, and we're fine, and we want to use that. Great, we found it. Okay, now let's look. We put it in a subdirectory, external boost, so that it's nicely modularized. You could have called the find package command from every subdirectory where you need it, but that's redundant. You're looking for the same libraries over and over again, and especially it takes a lot of time. If you have a big project like we have in our company, and you're doing this, this really, really makes your CMaking process quite long. You don't want to have that, at least if you know beforehand what of the libraries you require in your whole project. So we do this in one directory. Fine. But now, one thing, the important targets, as I said, they propagate their usage requirements automatically like modern CMake should do. Okay, now we are in a subdirectory, and for that we would prefer to go from the, you see it on the left-hand side, the topmost CMake list script there, and just using the command add subdirectory, go into the external subdirectory, and there again calling add subdirectory to go to the boost and then get there all the things. But sadly, this does not work as we expect it to. Instead, we have to use the so-called include command to verbatimly copy the content of the boost CMake list txt file in the topmost CMake list txt file, because add subdirectory cannot propagate the targets upwards, because targets as well as variables, by definition, when they come back from find package, they have local scope, which means they are known in this directory, they are known as subdirectories, but not in the ones above. For a good reason, as I said, it could be the case that you're calling the script, the find package command for boost from several subdirectories, and you don't want to have name clashes then. But in our case, this is not what we want. And using include there helps, but it's not beautiful, it's not what we want. We shouldn't care in the topmost directory what we have to get there. If there are more external libraries, we have to do a lot of stuff there with include. That's not what we want. That's too much. That's redundant. Let's just do it in one directory where it should belong, modularization, you know all the stuff. So another thing would be better. And can we do better? And yes, we can, using the more modern CMake approach. Because since CMake 3.11, it is now possible to promote imported targets to global scope just by setting the imported global property using the set target properties command. You see it on the right hand side. It's the same find package script we've seen before, the CMake lists txt file from the boost subdirectory, just the part on the bottom added. So if we find them, we just say, okay, we make them global now. Now they are global targets like all other targets that you can build already are. And then we are fine. Perfect. Just one note, you cannot demote them later again. So either if you promoted them afterwards or if you created important targets from the beginning as global, you cannot demote them. Have to keep that in mind. The thing that might happen if you promote them, that you can have name clashes, and then you should of course resolve them, but that's a simple task in general. So as I said, don't call the same script in subdirectories, call it just in one directory and use it from there, and then make it global so that everyone sees the targets and you're fine. So now we found boost. That's great. Let's go on to the next dependency. And, oh no, wait a second. Let's just check. Now we can use the add subdirectory call as we wanted, and we are fine. We are fine there. Don't have to use include anymore. Looks cleaner. That's perfect. Just keep in mind, this only works with modern CMake because it works with imported targets, and even with a more modern CMake approach, because you need this possibility to set this set this requirement to make it global. For variables, it's not possible to promote them. You can, of course, somehow copy them further, but that's not really nice. You don't want to go this way. Stick to that. Okay, now we found boost. We get it everywhere, the targets we need. Perfect, let's go on, trying to look for a boost outcome. And in this case, we don't have a fine script. We have to create the imported targets that we want ourselves by hand. And for that, we even try in traditional CMake to create imported targets because they also already existed there. And for that, we have the add library command, for which you can create targets which are shared libraries, static libraries, but it's also possible to create it for to create imported targets and for other types. In our case, boost outcome is a header-only library, so it's neither static nor shared. So what should we use? Luckily, there's the keyword unknown. But still, that's not really pleasant. That's not what we want to have. But okay, that's what we have to use, and that's what works in traditional CMake. And then, as we said, maybe we can try to make these imported targets to carry their own usage requirements as well as it should be done in modern CMake. So let's set some requirement. Okay, I create one myself, which is called my_include_dirs, which will contain the path to the include directory there, and set it on as and set this property on that particular target. And similar for some compile features. In this case, boost outcome requires C++14, so I have to mention this somehow, and I do it here and just adding the string that I want later added to the command line so that the compiler uses C++14. It's working, but it's not so nice. But at least I can set these requirements. Have to keep in mind they are not automatically propagated. I have to do it myself later. But it's sad that that I'm required to set some custom properties. Aren't there something that I could use? And in modern CMake there is. There is the so-called interface include_dirs and interface compile features that you could set. Note in line 18 you see there's even a special case for requiring C++14. So which is better than just verbatimly have the command that you should put to the compiler's command line later. CMake will figure out what the right command is in this case. And note something different there in line 10. We can even now say, hey, this is an interface. It's a header-only library. There's a special keyword for it now instead of using unknown. So that's good. That's fine. But still, that's not what we are supposed to do in modern CMake. Shouldn't we use the target underscore commands? And yes, I would say we should use them. And why doesn't it work? Or can we maybe do better? And yes, also with more modern CMake, starting from CMake 3.11, we can do that. Because now the target underscore commands also work with imported targets. So now you see it on the right-hand side. Instead of using sec target properties and writing out the property we are setting it on, we are using the target include_dirs to directly say, okay, we want to set an include directory. And we use the keyword interface to say, okay, that's a usage requirement. We want to set it as usage requirement, not as build requirement, which, by the way, wouldn't work for imported target because it's nothing you can build. It's built already. Similar for the target compile features, we use that command and setting as a usage requirement. So that's nice that we want. And now we can even do more. We can do aliasing. We can create an alias. So in our case here, as I said, boost outcome, it's already reviewed. It's part of boost, but it's not released. So maybe just let's say that it is like this. So I'm changing the name there. But at the end, I want the user not to care if it's my reviewed version that I found somewhere else or if it's coming from the find boost script. So I'm using something which has probably the similar syntax there. I'm creating a target for it, which is called boost : outcome. And that's just a read-only, by the way, it's read-only, alias for the name I chose beforehand. So this is nice. I can do that now. And this didn't work before. So that's good. Yes? Okay, the question is, what is the system keyword doing there in line 14? That's even a little bit more than we did before. We are saying now, okay, this is a system header, so if there are coming warnings from this, please ignore them. I don't care about the warnings coming from that library. In this case, for example, if you know GCC, it has the -i flag for includes and has the -i system flag, I think it's called, for system includes, which you don't care about the warnings because you think, okay, if there are warnings, still, it should be fine. That's what I'm doing here because I don't want to don't want to fix the errors in boost outcome, want to just fix my errors and my warnings and everything. But good that you know it. I forgot about that. Okay, now we found all the libraries. That's fine, our extended dependencies. Let's go on creating the ones we want to create, our common libraries, which are basic math and the extended math library. Okay, and for that we're doing the following thing in the library subdirectory, and we're done. It's overwhelming, isn't it? So that's traditional CMake. Let's look at it step by step, and let's see if we can do better, maybe. Okay. First, the general stuff. At line 3, we say, okay, that's the minimum required version we are using of CMake. In this case, it's traditional 1.2.8.10. We have at least, and then say, okay, this project has this name, some version, some description, which is nice. Okay, interesting part starts at line 10. Now we are saying, okay, this is a variable, and the following things stored in this variable are my sources. Great. And then we are creating, what is that, an object library there in line 16, giving you the sources. Why are we creating an object library, and what, by the way, is that? We could have just, we want to create 2 libraries and could just edit the sources twice, but we are not doing this. Okay, the reason is, if you look at line 12, it's called heavy math CPP, has probably some really hardcore template foo magic in there and takes ages to compile. I don't want to compile it twice if I don't have to. So let's just compile it once into object files and then use an object target library there, object library, as a handle for the collection of object files I just compiled. And that is what object libraries are for. So that's good. We don't have to compile it twice. Fine, perfect. And in modern CMake, we would do similar, just a little bit different. We have the target sources command here in line 12, where we can be more specific to say, okay, these sources are private just for building, while this here is public, it's needed for building and for using, and the last one, it's interface, so that's just needed for using. We can be more specific there, that's good, and even the order looks better. First we declare what we want to build, and then we add the sources. That's great, perfect. Oh, wait a second. We have some dummy variable there. Why is that? Oh yeah, some dummy source, because the add library command, it requires at least one source file. Even if we now have the target sources command, that's inconvenient. That's not what we want, especially if I'm using a dummy here. I need to have the dummy in the file system too, or CMake will complain that it cannot find it, or I have to just move one of the sources up. That's not nice, so can't we do better? And with modern CMake, again starting from CMake 3.11, it's now possible to just get rid of this additional source file. So now we can say, okay, declare this library, in this case an object library, with no sources, and add the sources later. However, you should not forget to add these sources, or CMake will complain that you forgot this, which is a good thing, so it reminds you. But it looks cleaner, it's easier, and why shouldn't we go this way? And especially it also works now for the add executable command, which is the same thing, just for creating executables. Great, good. And then if we have that, we want to add some usage requirements maybe. So in this case, we have some requirements for the include directory, and we have some compile flags, because what is it? Oh, okay, my library requires const expr support, so it seems to require at least C++11. We should add this. And how do we do this? For the include directory, we use include directories. That's traditional CMake, which means we are setting this on the environment, which also means not only the one target we are setting it for, but all targets declared in this CMake list txt file will know this. Might be inconvenient, but okay, that's how it is. But, oh no, wait, it's just setting the build requirement. I wanted to set the usage requirements too, so this doesn't work. So we have to keep in mind to later when we're using it, somehow get the usage requirements there. So extract it again and set it by hand, as I said. That's unfortunate, but okay, that's how we have to go in traditional CMake. And similar for the compile feature. Over there we don't even have a special command for that, or no requirement, no property which we can set, but okay, we can use the cache variable, the CMake CSX flags, and set it there, so that in this case now, oh yeah, everyone every target that is compiled now requires C++11. That's not really what I want. Can we do better? And with modern CMake, as you have seen before, we can be more explicit and more target-centric and just use the target include directories command to just set this directory, this include search path for this library. And as we're using the keyword public there in line 20, we're setting it as build as well as usage requirement. And similar for the target compile feature, we're setting that feature. And note, we even have a special feature for requiring a compiler, which running a compiler in the mode where the CXX const expr is supported. So it doesn't have to be C++11. It can be an older compiler, which at least supports that. I think in Visual Studio you might have this case sometimes. Nowadays it's not so much important anymore, but still that's better. It looks good. And fine, okay, now we set the usage requirements there, but maybe it also has some dependencies too, and they have usage requirements too. And in this case, we have a dependency on boost outcome. And remember, we set some custom variables, some custom properties there. The my compile features, for example, we are extracting it in line 26 with the get target property, storing it in the variable props, and then in line 27, 28, we're adding it to our CMake CXX flags cache variable, so that we don't forget in this case, oh yeah, remember now it requires C++14, so now we have to use C++14, not 11 again. If the order is wrong, then it might not compile, that's inconvenient. And there's something nice there in line 25. You see we are using so-called generator expressions. And thereby we are just saying, okay, this is special syntax there. Get me the target property from boost outcome, which is called my include dirs, and then from this one, get me the value. And that is what we automatically stuff there into the include directories command and set it as a system, as a system include there. So similar as we did before. You remember your question with the system. And okay, that's how we get the build requirement there for using boost outcome. That is good. And okay, fine. However, how do we do that in modern CMake? And the thing is, we can use the target include directories command and target compile features, but actually we just have to do the same. Just in the second case, at least we can also use the generator expression, but still we have to extract it from the special property we have for that. We have to extract it by hand. That's inconvenient. Why do I have to repeat this stuff? Shouldn't I just declare a dependency on boost outcome and be done? That's what modern CMake is for. But sadly, this doesn't work with object libraries in modern CMake. However, luckily, it works with more modern CMake. Starting from CMake 3.12, it is now possible to use the target link libraries command, which you use to declare a dependency on other targets, with object targets. So in this case, we are saying, okay, our object target on the left-hand side has a public dependency. You see it on the right-hand side in line 25 on boost outcome, and we're done. So instead of doing 1, 2, 3, 4, 5 lines plus 6, 1 if you take the command there, no, the comment is on both sides, forget that. So instead of using 5 lines, we're just using 1. It looks cleaner, less possibilities to make errors. That is good, that looks nice. So that's good, perfect. Now we can set the usage requirements for dependencies and can propagate them to object targets. Great. How about the other way around? If we have an object target, which is a dependency, we might need this later for our variables. So let's look at that. That's a little bit more interesting, I guess. And by the subtitle, you might realize there's something special about it. So let's see. I have a short quiz for you. This is a short program, or not program, but a short CMake list TXT file. I will explain it briefly, and then I will have 2 questions for you. Maybe you find the right answers. Okay, starting on the top, we are just declaring a common object library, which probably everyone else in that target, in that CMake list TXT file should use. It has some source, common CPP. It has some include search directory, the include common, it's called. Fine. Then in line 7, we declare a shared library. No sources, that's nice. We can do this in more modern CMake now. Great. It doesn't have any dependency yet, so it's fine. We just declared it. And then in line 10 till 12 and 14 to 16, we're declaring 2 more object libraries with their own source and their own include directory. Perfect. Okay, now we have that. And the interesting parts for the questions are lines 19 till 21. There we are declaring a dependency using different keywords, as you see. And we say here the shared library has a public dependency. So we remember public means, okay, setting build and usage requirements on the common object lib, while the object lib 2 has a private dependency, setting build requirements, okay, on the common object lib, and object lib 3 has an interface dependency, you know that, usage requirement. Okay, perfect. And these 3 libraries there on the left-hand side, the shared and the two object libs, they later will then be linked into their respective executable targets. So exe1 will be linked to shared lib 1, exe2 will be linked to object lib 2, and exe3 will be linked to object lib 3. So far, so good. I hope everyone understands how this is created. Okay, now my first question. What do you think? Which of the local include directories, by this I don't mean the ones automatically coming from the compiler, so pointing to some system headers or something like that, which of these local include directories does each of the individual targets, exe1, exe2, exe3, know during their compilation? Does anyone has a clue? Just speak up if you think you know that. Okay, no problem, I'll tell you.
I guess no, it will know, it didn't know about any of the.
You think it will not know anything? No, that's not correct. I'll tell you, it's quite easy to understand, and that's how everything works there in general with propagation of usage requirement. exe1, let's look at that one. That's linking to shared library. So we have to look at the usage requirements of shared library. Shared library itself doesn't have a special requirement. It just gets them maybe propagated from common object lib. So let's look. It's using the keyword public. Okay, so its usage requirements will be set to. And from common object lib, there comes the include common. Perfect. Oh, there. One thing more. Every of these targets, of course, know their current directory. But we don't care about that. The interesting part is after the first AND. So through the shared library's usage requirement, we get include common. Let's look at exe2. It links against object lib 2. It has a private dependency on common object lib, which means the build requirements, but not its usage requirements, will be filled with the usage requirements from common object lib. So forget common object lib. It's just the includes 2 directory coming directly from the object lib 2. Fine, that looks logical. And similar for object lib 3, the one it brings itself, which is include 3, and the one it automatically gets from common object lib, because we're saying using the interface keyword there, set the usage requirement and fill my usage requirements into there. So that's why exe3 knows include common 2. Fine, hope that's somehow understandable. Now, what do you think? Which of these executable targets at the end will contain the object files coming from the common object lib, so for common.cpp? Does anyone has an idea what would be logical or what is probably right? Sorry, what? Repeat it, please.
exe1.
exe1, you think. Why do you think so? Okay. One should think, why should this be different than propagating of all the other usage requirements? But the thing is, it is different. So the correct answer would be none. Only the shared library itself gets the object files from common object libs. The other ones don't. So let's look at it real quick. Shared lib has a public dependency, so it means its build dependencies are set. So that might be the reason. Object lib 2 has also the build requirements set, but why isn't it? And object lib 3, okay, it's only usage requirements, so it doesn't set it there, but maybe it should have propagated it further, so that doesn't make sense, maybe. So why is that so? And I will try to explain, and I know that's not so easy, so let's just repeat what we have before for general usage requirements. For that, the line below is the important thing. The usage requirements of any target, even object library targets, on the right-hand side of our target link libraries are propagated to the ones on the left-hand side. depending on the keyword. So with using private keyword, we are saying our usage requirement from the target on the right-hand side becomes the build requirement on the target on the left-hand side, in this case our object target. Similar for interface, we're saying the usage requirement from right-hand side becomes usage requirement from left-hand side, and for public it's both. We said both. We had this. Fine. That's like it should be all the time. That's for all targets the same. And now the interesting part, why doesn't it work for object files? And the thing is, object files are only ever propagated to direct dependence, which means you never fill the usage requirements of the target on the left-hand side. You can only set the build requirements. But still, there's an additional exception to that reason, to that case, and that's only if the target on the left-hand side is not an object target itself. The reason for that is to prevent double linking against object files, and at the end have multiple references errors from the linker. This is currently highly debated because a lot of people, you probably too, don't think this is too logical and should be a way around this, and it's discussed, and maybe this will be fixed in a later version, but currently that's how it is, how it was decided and how it was implemented. So let's look real quick. If you have object files on the right-hand side and you have the private keyword, and on the left-hand side there's not an object files, it gets into its build requirement, while if there's an object file, there's no propagation at all of object files. While if there's the interface keyword, you don't propagate, no matter what kind of target is on the left-hand side. And with the public keyword, it's similar as if you write private there regarding the object file. So you have to keep that in mind. Okay, these are the interesting quirks that we have there. And this is the interesting thing with the one below. Okay. Basic math, extended math continues. We have this year had the left stuff we have covered. We have our object library. Now let's create the shared libraries there. And let's look at this. First, we are extracting the object files, in this case from because traditional CMake doesn't have the support for linking using the target link library to object files. We have to extract the object target, sorry. We have to extract the object files from the object target and add it as sources there and create it. On modern CMake, it would look like this. We just have to do the same, but use the target sources command. While then we have to set some usage requirements for our shared library. But as I set them already for the object files before, and on directory scope, and they're pretty much the same. I don't have to do anything here. So might be nice, but maybe I should be more specific. On modern CMake, I can be more specific, so I'm setting the dependencies here, saying, okay, you get propagated the interface include directories, the requirement from this property, which means it's the include search directory from the usage requirement of our object lib. Add this to our object target, to our shared library, sorry, as a build and as a usage requirement, similar for compiler. So we have to propagate this stuff by hand. This is not nice, but as you know, as you've seen, we can use now target link library, and instead of doing all the stuff on the left-hand side, we just do the simple single line and saying our basic math library has a dependency on basic math object lib on our object library. It's a public dependency, so the build as well as the usage requirements are set. We're done. Fine, that looks good. That's what we want. Okay, and similar for our our extended math library there, it gets some extra source file. That's probably the premium content there, the extended functionality. And of course, we remember it has some extra dependency, in this case on Boost Graph. So we have to add the include directory for Boost Graph and the link file there. However, remember the Boost libraries variable does not only contain the path to the Boost Graph library, it also contains the path to the Boost program options library we found before. So it even gets more. But luckily, most of the time, the linker is smart enough to figure that out. But we shouldn't do that in general. We don't have to. It shouldn't be the case. And in modern CMake, it looks similar. We do the same stuff, very verbose there, getting everything over by hand from the object library, and then at the end, at least, linking or having the dependency on our Boost Graph library. That's simpler, and we even have some space left for creating a nice alias there, so which we could use later. That's nice. And yeah, that is that. And with CMake 3.12, it still looks smaller. Now it's just one line instead of all the ones. We've seen this before. One extra line, or you can combine them in one target link libraries call for the dependency on boost graph. And then the alias is the same. So that's nice. That's perfect. That's good. So we're done. So now we have our libraries. From going this way in traditional CMake, we went over modern CMake. Have to do more stuff. Now it's 60. Before it was maybe just 41. I don't know. Let's see. It was 49 lines. Now it's 60 lines. Okay, we have 2 lines extra there for the alias, but still it's a lot of stuff to do. And with more modern CMake, it looks better. We only have 41 lines and even have the alias. So that looks smart. We use the functionality of automatic propagation of dependency requirements, usage requirements, so that is what we want. Okay, now we are almost done. Let's link everything together into our executables, our free calculator and the premium calculator. And that is how we do it in traditional CMake. In line 20, no, what is it, line 10, sorry, we create the free calculator, give it some sources, add some dependency there on our library. You see, we can use now the target link library, which has a dependency, declares a dependency on basic math library we just created before. It doesn't use the keyword. Remember, it's traditional CMake there. Then we do the same on line 19 to 21 for our extended, of our premium calculator, which links to the extended math library. And that one also gets some, it possibly gets some extra sources, which are coming there from line 14 till 16. So what does it do? If that file exists, then add it to the sources and compile it to keyfile.cpp. Maybe these are some blacklisted serial keys that some hackers already know and you want to blacklist them or something. It depends on what you're going for. So you can do that too, optional, adding that's optional. In modern CMake, it looks pretty much the same, but it can be a little easier. We shouldn't forget at the bottom the dependency to boost program options. On the right-hand side, we're doing this in one call in line 12 to 14, for example, using target link libraries, and in line 9 till 21 too. But now we changed the order. First, we declare our variable there, adding the dependencies, and then adding the optional source file at the bottom. So this looks a little bit easier to read, but nothing fancy. And of course, this dummy CPP file with more modern CMake, we can get rid of this one. So this is the version which is more modern. Not a big difference, but okay, fine. Now we're done. That's great. Let's see if it compiles and does what we want. Let's start with the modern and more modern way. First, let's CMaking it. Looks good. Everything, and then let's compile it. Perfect, 100%. We are creating all our targets. Our program is done. That's what we wanted. We succeeded in doing this in a simpler way with more modern CMake. So just for the heck of it, let's try if we could do the same in traditional CMake. CMaking looks good, almost the same. And then, of course, compiling would... Oh, no, what's that? We have a missing... we cannot find the include file, math.h. That one comes from... I remember it comes from our library. So that's from the library subdirectory. But why doesn't it find it? Oh, yeah, right. We forgot. We only set the build requirements with the... We only set the build requirements with the include search path, not the usage requirements. We have to propagate them by hand, so we have to add this there. And this is not really nice. So in line 31, we have to add a relative path there to link to that. So we have to know the directory structure in this directory, although we don't want to. And in line 32, 33, we are also adding the include search path for boost outcome, because that is also not propagated automatically. That is not what we really wanted, but luckily in modern CMake, on more modern CMake, we don't have to do that. That's just one of the traditional CMake things, quirks we have to work around. So let's check if it now compiles. Hopefully CMaking still works and compiling. Oh, finally, we're done. That is great. Okay, we use target link libraries. I mention it quite often, and I also mentioned it's quite old. And because of that, there are some things you have to keep in mind, and I will quickly show you. This does not work. What do we do here? We create in one directory a target, some target, and from another directory we add a private dependency. So we are trying to set a set the build requirement from another directory. This does not work. This is inconvenient, but okay, maybe it's not so bad, and we just never shouldn't do this, and the compiler and the CMake will tell us. However, if we by accident or so try to set the usage requirement from another directory, this works. This is not right, and it wasn't intended by CMake. And the reason that preventing setting any of the requirements from outside was because in the old ways of CMake, this would have had some weird effect and shouldn't be possible. And now there's no reason for it anymore. And so luckily, with the upcoming version, which is 3.13, this restriction is lifted, and now it's possible, if you want to add a dependency from another directory to a target. And similar with that, we had the same problem with install, which is for installing our targets to some directory. We only could call this from the same directory where we created the target. Now it's possible to call it from somewhere else. So it's the possibility to better use modularization in our CMake file. So that's probably nice. So maybe there's something more we can fix in future versions. So let's see, maybe, oh yeah, there's something that was fixed. I mentioned that briefly. Aliasing imported targets is now working, except for the ones which are declared as unknown, which are neither shared nor static nor interface nor module nor whatever there is. I forgot. Unknown doesn't work. It was an oversight. So this should hopefully be fixed. And as far as I know, they already have a fix for it, or maybe not. At least there's an issue. That is good. So if you want to get this fixed, you can do that. That's perfect, if you wouldn't. And then again, we've seen the quirks and the weird things with the propagation of object files from object libraries. Maybe we should change that. That was decided to be the first step so that this works and don't introduce too many changes, but maybe we shouldn't have done that. So there's some ideas for lifting this problem and also allowing circular dependencies. And CMake must have some knowledge about this to take care of it, but maybe this is done. And so there are at least two issues I know of to make them simpler. I'm not sure if there are already some merge or pull requests for it, but still, if you want this lifted, and so you should try to come up with some solution. By the way, it's possible because CMake is written in C++, and nowadays it's even written in C++11 at least. So you can use modern C++ for doing that. You see, everything is at least modern here. And now there's also another idea which should be extended maybe. There's the so-called add custom command from CMake. Which doesn't work the same with object targets. So object targets are still a special beast in some cases. For example, you have the possibility to use add custom command with a pre-built or post-built keyword there to do something before building or after building. I think it even has some pre-link so that you do something before linking. And that would be great in some cases if you could do this similar for object files. For example, stripping them if they are too large or so, because you have too many symbols there and you couldn't get them out before or whatever reason. There might be some reasons to do something beforehand, but sadly this doesn't work with object targets. So maybe someone should try to fix this. There's at least an issue. That's one I did because I stumbled across this and thought that maybe someone can change this. I didn't want to. I tackled some other things, the ones you've seen, by the way. And so let's wrap it up. Now we have something seen that we can do, something which should maybe be done later. So what should you take home from here, from this talk? And I would say switch to switch to more modern CMake. Adopt this, because especially it is cleaner to use. The code that you create in CMake, it's smaller, and by doing that, it's in general less error prone. Especially, of course, than traditional CMake, but also than modern CMake with the older versions. And by that older versions, I mean try to use, at least I don't see any reason for not doing this, the newest CMake versions possible, or at least the only one version behind. So I would recommend to at least start with CMake 3.12, because from then on you can use the object targets more naturally. And there's actually, if you have some code base which is traditional CMake or modern CMake but doesn't support especially this compiler, it doesn't really matter, because CMake is really, really good in keeping backwards compatibility. So there's no problem with using the newest ones. And if you don't have it on your system, you can either download a precompiled version from the CMake website, or you can build it yourself. It's not really difficult. The only thing you need to have is some quite old CMake version, I guess, at least 2.8.12, I think you require, and CMake and a C++11 able compiler, and that's it. And then you can compile your own version, and that's a thing I would recommend if you have no other way to get the new version. And if you use the new version, and so the more modern CMake style, I always would recommend to create your targets first without any sources, and then use the target sources command and all the other target underscore commands to add the build and usage requirements. Use imported targets if you have external libraries, either by getting them automatically from the find packages, like we've seen with the Boost library collection there, or doing it yourself, as I've presented here with Boost Outcome. There's even some possibility, if you have some packages, maybe you build them or somewhere else, who export some of their targets into a special file, you can just include that, or I'm not sure what the command is, but you can use that, and then you have the targets available to link against and use them, and that's also a good way. Never try to hard code the library directly. Just if you use target linked libraries and then the name of that library and not of the target, then you will link to the file directly if you find it in the system's path variable. But if you are another system, that wouldn't work, and so that's not what you should go. Go with a modern approach. Use targets, use imported targets in this case. And with that, I would say, if you find something which is not appealing to you, which you think, why should I work around this problem? Why can't I fix this? Look, maybe there is an issue for it, contribute to it, maybe have some ideas. Maybe there's no issue, write your own issue for that. And even maybe you can go a little further and find some way to extend CMake to support what you want and provide it as merge request. The community there is really responsive, they're really helpful, they help you a lot, and they know a lot of stuff, and even the original creators do a lot of stuff. And with that, I'm done. If you want to know more about modern and more modern CMake, I really highly recommend the ebook from Greg Scott, who, by the way, is one of the, as far as I know, the main developers, or at least lately one of the big developers there from CMake. Professional CMake, a practical guide. It's a really good book. I think about 480 slides. It costs, sadly, it costs something, but it's really worth it. It's $30 as far as I know. It's really a really good thing, and it even covers the topics I mentioned here, all the latest ones just briefly, but he covers them. If you don't want to pay money, there's the living document about modern CMake. You can read and contribute at this address. And if you are more the guy who wants to have some presentation, there are several online. The good one, one of the first ones, I think, is from Daniel Pfeiffer. It's called Effective CMake. Then there's Stephen Kelly, Embracing Modern CMake. And at this very conference last year was Mathieu Rupert, who did his Modern CMake for Modular Design talk, where he also mentioned some of the quirks we are now fixed, but also showed you how you use CMake to create your programs. And with that, I thank you very much for your attention. If you want to see the examples live or want to have the slides, you can find them under this address on GitHub. And with that, thank you very much. And if you have any questions, just fire them on me. We have 1 minute left. Sorry. Or no, we even have more. We have 5 because we started early, so you can go for.
Oh, actually, I have so many questions, honestly.
Oh.
But I will ask several of them. First of all, the Q&A you've showed us, will it actually compile with the 3 shared libraries and stuff? My question is there was a shared library, right? And we know
Yeah.
that shared library you need to compile about the object file as a position-independent code. And executable, when you use objects, you don't want that, right? So does it compile it twice? Does it work? Is there any, like the way for
Wait a
this?
second, there is some, where do I have it? No, where is that?
So, I mean, in my work, we just declare two libraries, one static and shared, or whatever, to work around this problem, to explicitly compile it twice. So
okay.
how does it work with the...
In this case, we're using the position-independent code CMake variable there. You see it on the topmost CMake list file on the left-hand side. And
But
it's set in line 10.
you kind of don't want it, like, in executable, if you have it, and you want, like, avoid this, because it's at indirection layer and stuff. So, generally speaking, like, you should not do it if you care about performance.
To be honest, I cannot really answer this in detail. I just know that this one here is specific. So if you're compiling the library using this option there, then it adds the -f pick flag, and on executables the -f PIE flag. But I'm not really sure if all of this works. If you probably then not, as you said, if you don't want to use that.
Right.
But of course, you could just remove that and not build shared libraries. You could build static libraries. It would be the same, just have to either change the share to static, what we had there, or you can just remove it entirely and use the CMake variable, what was it called? Build shared lib, I forgot it.
Build shared libs.
Something like that, which you can set globally, and it either will build shared or static library depending on the value of this variable. But except for that, I really cannot answer that. Sorry.
Okay. No. Actually, we asked about Q&A you had, like with 3 libraries and stuff, because they're like better example, but nevertheless. And this a second question is like the CMakes. Does it, if you still put like include directories, does it propagate like properties for directory, or does it put it into a target? In the new CMake, because like, is there a way? My question is because sometimes you want to like gather all the build flags for a target, and then in old CMake you need to go CXX flags of your mode, and you go directories,
and that's what I wanted to
target.
show you here. With modern CMake, you should actually never touch CMake CXX flags, because that's something the user that wants to use your library should touch.
Does it still impact this? So do they still have effect?
Of course, if you're setting the CMake CXX flags, it has some impact on this. And it then depends on the order the compiler gets these variables. Actually, I don't know in what order this will happen, but I would just recommend don't touch the CMake CXX flags variable if you don't have to, and use the modern approach. And if you have to stick with traditional CMake, you have to keep in common by using the include directories. You're setting on directory scope, so every target knows this, but it's only the build requirement, not the user requirement.
Okay, thank you.
Okay, you're welcome. Any more questions?
Well,
Or we are
in
done?
this case, I have a question.
Okay, yeah, go ahead.
In our company, we are required from one specific C++ version, so still C++ 11. So you showed always we should pass the requirements into the target.
Yeah.
What's the preferred way in with specific rule sets for a company?
Good question. At least this one here in general is agnostic to the compiler and C++ version you're using. The versions I was just using because the dependencies used them, so we had this requirement. But if you're requiring some special compile feature, there are, at least starting from C++ 11, there's a special list. There's not only this CXX standard 14 you can see right now, but there the one CXX underscore const expert for all these constructs there. There's also something which requires C++ 98 and maybe 03 too, I'm not sure about that. But I think these specific explicit targets there you only have for C++ 11. Now they're going away from that again because it's too much hassle. They just say, okay, require C++ 17 and you're done. If you have something else, you probably have to find some other way, or just do it inside C++ with the functionality the standard gives you for testing if your compiler supports this functionality, or you have these headers and so on. But sadly, I don't really have an answer for you there. Sorry.
I think you can always use the try compile function. I think you can use the try compile function.
Okay,
if I
then.
recall correctly.
Okay, I think the mic is out, but you said you think you can always require to compile a function.
No. There's a try compile function.
Oh, the
if I
command try
recall
compile
correctly,
function.
that's how
Yes,
it's
you're
called.
right.
You specify the code, it tries to compile it. If it's okay, the output variable will be true, so you can use it.
Yes, you're right. There's this try compile, and there are other commands which you could test that might help in this case. I played around with this once, and it has been some time ago, and then I tried to fix the problems I had there. So there are ways, but they are also quite quirky. So if you find some better ways, provide them as merge requests to CMake and make it better. I think we are run out of time. Thank you very much for your attention.
Thank you.
It's a pleasure being here.